How are you?
Good. It's kind of like Friday, so.
That was nice.
Yeah.
Friday's always a good day.
Yeah. Yeah, unless you work.
Yeah.
Thank you, getting your present for recording the lectures.
What?
It's incredible.
What is it?
Recording the lectures.
Oh, you're welcome.
What?
What? Was I trying to figure out what?
I don't think you should be scheduled.
What you were going to give me? Oh, did you say you had something
I think I
for
have
me?
to come in
Or thank you
tomorrow.
for
To
recording?
open can stay open until.
Oh, okay. In your personal life?
Yeah, I'm gonna have to go long walk.
You're thinking of doing it?
Maybe you're a present because you record the lecture.
Oh, that's not necessary. It's my pleasure. Thank you for the thought, though. Appreciate it.
That too.
Do y'all have any homework questions? Yeah.
Section 3.1, number 12A.
Number 1, 12A. Make sure I'm in this one. Y'all see that? Find the derivative of the given function and evaluate at the given point. So in 3.3, we'll start to look at shortcuts to evaluate a derivative. Right now, I guess we really have 3 options to determine the derivative of this function. So 1, we could use the limit as x approaches a on f of x minus f of a over x minus a. Alternatively, the limit as h approaches 0, f of a plus h minus f of a all over h. Okay, all right. And really with the technique we saw in 3.2, there's a third way we could find the derivative. So I'm just going to put this here to remind ourselves, although these are the 2 techniques we saw, or definitions we saw in 3.1, these both give us the derivative at a point, the point a comma f of a. So those two will output a single number, which is, remember the derivative is just another name for the slope of the tangent line, the slope of the tangent line at a given point. The output is a number. And then in 3.2, we looked at the derivative as a function of x, where we modified the second definition at a point so that we could get an actual function of x instead of a number. All right, so we're using the second one. Okay. So first of all, let's identify what a is given to us in this problem. What is a? A is -1.
The first part wanted us to find f prime of x.
F prime of x. Well, that's strange because your textbook doesn't talk. We don't talk about f prime of x until 3.2. So that's kind of weird. So then if we need to find f prime, then we go, this is section 3.1, and we have to go to section 3.2, where it says the definition of the derivative, the limit as h goes to 0 on you might think of this as the difference quotient, the limit as h approaches 0 on the difference quotient. Again, built into the definition, we see explicitly, once we compute the limit, what it's outputting. It's outputting f prime of x. It's outputting a function of x, which is the derivative at all x values on the given function f of x. So we'll use that one. Three x squared minus 2x. Okay. So you're always given a function to compute a derivative. The only thing in this definition that we need to compute outside of simplifying the quotient is the f of x plus h. So let's compute f of x plus h. And our function is 3 times the input squared minus 2 times the input. So you can simplify this now. It's probably easier. It's less stuff to have to put up in the definition. Or you could just put it all in and simplify it later. Let's go ahead and simplify this now. So we have 3 times x squared, 3 times 2xh, and 3 times h squared. And then we have a minus 2x and a minus 2h. So unfortunately, there's nothing there to simplify. We're going to have to wait till we put it into the definition and cancel some things with f of x. Anybody have any questions on this? It's f of x plus h. And we're going to put this into our definition. So the derivative is the limit as h goes to 0 on all of that stuff. Minus f of x and then we have all of this over h. And we'll combine like terms. We've got a 3x squared minus 3x squared. So that and that are gone. And we have a positive 2x and a negative 2x. So what we're left with up top is 6xh plus 3h squared minus 2h all over h. Again, just an algebraic thing to remember, don't just cross one h out of one term in the numerator. All 3 terms in the numerator are divided by h. So that simplifies to the limit h approaches 0, 6x plus 3h minus 2. As h goes to 0, it only affects this 3h, so that's going to 0 as well, and we're left with 6x minus 2 as our derivative. Do you have any questions? Yeah.
Is it possible for the h to ever get left in there? Like, will we ever see that? Or is it not a derivative if the h remains?
Yeah, if the h remains, you've probably done something wrong, because, we go back up to our definition, when we compute all of this, what we should end up with is just a function of x only.
Okay.
So if you've got an h in there, you did something wrong.
Okay.
And so with other functions like logarithms or trig functions, finding their derivative using the definition isn't really a trivial thing. It's with polynomials and such, it's kind of easy because we just combine like terms and cancel out the h. But you could imagine with more complicated functions how difficult it might be to compute a derivative using the definition of the derivative. Which is why we spend a whole lot of time in Chapter 3 talking about shortcut methods. So that's our derivative, and then they want us to find the derivative function and then evaluate at the given point. So we've got our derivative function, I guess this is part A, we'll call that, and then part B, it just says evaluate f prime of x at the point -1, what was it, -1, 5? Well, the derivative only inputs x, our x value is 1, so all we need to do here is find f prime of -1. The -6 minus 2. So what does -8 represent? The slope of the tangent line. -8 is the slope of the tangent line on the function 3x squared minus 2x at the specific point -1, 5. In other words, another way to think about that is if I wanted to know how steep that function is at this particular location, I can measure the steepness as -8. Does all that make sense? Do y'all have any questions on that? Are there any other homework questions? I would recommend, if you have the time, as always, to keep up with the homework as we progress through class, because there's these homeworks, there's 11 sections in Chapter 3, and they all go really quickly. Technically, we're supposed to start at the end of class, we're supposed to start 3.5 today, so we move through these sections rapidly. In each section, you get at least one new way to take a derivative. In 3.2, we left off, well, we've already looked at the definition of the derivative function. Then we started talking about how do we graph the derivative? What does the derivative look like for a particular function that's given? So there's really 4 things we're looking at mentioned here, and keep this diagram in mind. If we're graphing the derivative, as normal, anything above the x-axis is where the derivative is positive. Below is where the derivative is negative. On the x-axis, where the derivative is 0. Another way to think about the derivative or the slope of the tangent line being 0 is when you have a horizontal tangent line. So like at the vertex of a parabola is a pretty classic example of where you would have a horizontal tangent line. So here, the derivative at that point would equal 0. And typically, that's the thing we look for first. We look for the zeros or the x-intercepts first. because we know outside and in between the x-intercepts, the graph will be either above or below the x-axis. Another thing we want to pay attention to is when the slope of the tangent line is undefined, which we haven't talked about, but it's mentioned here right below this. So whenever any A, B, or C happens, you will either have an asymptote or a hole on the graph of the derivative. So we already know how to represent visually when a function's undefined somewhere that's not changing. We've got to sort of recalculate what we think about when we're graphing the derivative, though. So the derivative is undefined if the function is not continuous at a particular point A, or x value A, if the function has a corner, or if the function has a vertical tangent. So not being continuous, we talked extensively about continuity in 2.6. An example of that is this first figure. So this value here at A, there's no way to define a slope of a tangent line there because your function doesn't have, well, how should I say this? There's no way to define the slope of a tangent line here in figure 318 because why? Because of continuity. And if we think about continuity, what does that imply about the definition of the derivative? Yeah, the limit wouldn't exist because the definition of the derivative h is approaching 0. But that idea was, here we have some function, here's a plus h. As h goes to 0, the second point approaches the first point. But all we're saying is h is getting smaller and smaller. So that is a two-sided limit. We have to be able to approach, here's a minus h. We have to be able to approach a from both directions by the definition. Definition is two-sided. So I could define, like, at this point that included on the function, I could find the slope of this tangent line. But the problem is that as I come from the other direction, the slope of that tangent line is totally different from the slope of this tangent line. So the slope of this tangent line, totally different than the slope of this tangent line. Okay, and that's kind of directly related to why the derivative doesn't exist at a corner here in 319. The derivative doesn't exist at a corner because, again, the slopes of the two lines, they're not coinciding as the same line. So here with this line, it's a particular slope, call it M1, but this line has a completely different slope. Since those two slopes aren't the same, you can't define the derivative there. And if you think about this image here, where the slopes on this quadratic, the slopes of the tangent line, at every point they're all different, except when I get to the point at 0, it's flat from this direction, and it's flat from the other direction. So I don't know if you can visualize that. There's two rulers on the side of that parabola moving at the same rate. They both flatten out at that point. Okay, so that's a corner. Like the absolute value doesn't have a derivative at 0 because you've got the corner. And finally, the vertical tangent illustrated in 320A and 320B. There's two different functions that have a vertical tangent. A vertical tangent simply means you've got a vertical line that's describing the slope. So this vertical tangent here, for instance, tangent line's vertical, but as we look at all of these other tangent lines, as we get closer and closer to, what is that, x equals to 0, they start to become vertical. So derivative is undefined at all of these situations. In other words, if any of these situations occurs on a function when you graph the derivative, there's going to either be a hole or an asymptote on the graph of the derivative. Okay. So do y'all have any questions on any of this? So we have 4 examples where we're given the graph of a function, we want to graph its derivative. We're graphing f prime. The thing with the function itself and the derivative, the function and the derivative have the exact same inputs. So we're going to graph the derivative, we're going to think about the slope of the tangent line. In other words, if I put a ruler on this function, what's the slope at every single point doing? So let's just look at that first piece. We see that they're all linear pieces, but those slopes change. So from this piece, we just have to measure the slope. So what is the slope of that first piece in red? Right, we go from one point, we go down 2, and to the right 2. So it's -1. So no matter where you put your pencil, it's never going to change, right? Slope -1, slope's -1, slope's -1. So the slope of the tangent line, or the derivative, it's always -1. It's always constant on that piece. How do we graph a constant function? What does a constant function look like? It's a line, it's a horizontal line. So since on that piece the derivative always outputs -1, let's see if we can get this closer. Then we just have this as the graph of our derivative. Okay, but then we also have to think about what happens here at this corner. Does the derivative exist at the corner? No, so you've got the slopes of the tangent line are all -1 up until they get to that very point. So the way we illustrate that, this is of x value of -2. The way we illustrate that is with a hole. So we're illustrating the fact that the derivative is undefined at that point. Right, the point on the function is actually -2, but the output, the derivative is always -1. So the point on the derivative, it's still undefined when x is -2. Remember, they share the same x values, but the y value on the derivative is the slope of the tangent line. So that's why this point's at 2, -1. Sorry, -2, -1.
So the derivative is -1?
Yeah, the derivative is always -1 on that red segment
Only.
only.
So it says brackets derivative, would that be it, or would it not really have a derivative because it's not a constant function?
It does have a derivative, it's just a piecewise derivative. Because then when we move to this second piece, what's the slope on this second piece?
So it has multiple derivatives?
Yeah.
Gotcha, so that would be +1.
Yeah, so the slope here, well, is it? We go up 1 over 1. Slope here is always 1.
Would you be giving us something like that on the test?
Yeah, so on the test, it'll be, I'll probably format it so that it's a matching problem.
Will we be working more on this, or is it not out yet?
This is it. So the slope of the tangent line is -1. The y value of the tangent line on that piece is always, what was this one? Is always 1. But notice the slope of this piece being 1 starts really close to this corner and ends really close to this corner. So again, we're going to have, when we start, the derivative is undefined. And when we end, the derivative is undefined. That's still an x value of -2 on the left and an x value of 0 on the right. What's the y value on the derivative? 1, because the slope is always 1.
Do you know if there's a vertical asymptote on the derivative?
Vertical asymptote on the derivative occurs when the function has a vertical asymptote or we have a vertical tangent.
Okay.
So 320a and 320b. If a function looked like either one of those, you would the slope of your tangent line rather would be getting more and more vertical as you got closer and closer to a point. So again, if you visualize a ruler moving along this, it never changes. Once it hits this point, there's an abrupt change of the slope. It doesn't change along this path, then there's another abrupt change as it travels along this path. So what's the slope of this piece? Is what? -1/2. Okay, same thing happening here though. Right here, we can't define that derivative. That's an x value of 0. What's the y value? On the function is 4. What's the y value on the derivative? -1/2. The derivative is always outputting the slope. The slope is always -1/2. So let's say this is -1/2. X value of 0, and we continue this way. Do y'all have any questions on that? If we said, what's the derivative of this jigsaw or zigzag function at -4? The derivative of this function at -4 is -1, because that's the slope of that line when x is -4. Coming out here at -4, the slope is defined as -1. Out here at +4, the slope is defined as -1/2. So the graph looks weird because the function is weird in the sense of the slopes. Yeah.
So then, like say on a test question, if you asked us what would be at the point at, or the slope at -2, would that just be does not exist?
Yeah, so the derivative doesn't exist at an x value of -2 and at an x value of 0. So the way this would show up on the exam is I would give you the graph of the function and then somewhere have the graphs of derivatives. You just have to match the graph of the function to the graph of the derivative. Any other questions on this example? Okay, example 2. Enjoy this here. So g g of x, so this is g prime. So first of all, would there be anywhere on that graph the derivative doesn't exist? Do we see any corners? Do we see any places of discontinuity? And we don't see the tangent line getting horizontal, or sorry, vertical, right? So even way out here, tangent lines like that, way out here, tangent lines like that, it's not vertical. Do we see anywhere the derivative would be 0?
The two peaks
The two peaks,
on the trough.
okay. So here, somewhere around here, and somewhere around here. What do y'all think? A flat tangent line, horizontal tangent line there at those 3 points. Again, just imagine a pencil or a ruler traveling along this graph, measuring the slope. Once I get to this point, it's flat. It's flat again, right?
That means the derivative does not exist?
No. So at these 3 points, that means the derivative is what? 0, right? Is that straight? Can't tell. Close enough. That means that's the output. At those 3 points, the output on the derivative is 0. So we've got an x value of -3, a y value of 0, an x value of, let's say, -1, a y value of 0, and at +1, 0. Is everyone okay with that?
So the derivative is the x value? Right.
The derivative is the slope at that x value. The slope at the x value of -3 is 0, the slope at -1 is 0, and the slope at 1 is 0. So we're getting a horizontal tangent.
So one test would be like, what's the derivative of, no.
So just like with any other graph, once you have the zeros, right, so the idea was, okay, well, we have the zeros. On the left of the 0, the function's either up here doing something, or the function's down here doing something. In between the zeros, the function's doing something like that, or that, and then to the right, it's like that or like that, right? So that's what we're going to use to sort of separate the graph of G into different pieces. Okay, we know where it's 0. What happens to the left of this 0? So in other words, if we were putting at all of these points, if we're measuring the slope of the tangent line, at all of these points, what's happening? They're getting smaller, right? We know they eventually have to equal 0, but are all of these tangent lines positive or negative?
Some positive, some negative.
They're all negative. Oh, wait, no, they're all positive.
Right, the lines, all of those lines are like this. Some more exaggerated than the other, but all of these lines have a positive slope. Does everyone agree with that? So where's our derivative? It's above the x-axis, right? Because all of these slopes are positive. Do we start out kind of positive or a lot positive? Yeah, the slope of this line is a lot more positive than the slope of this line. So we start out really positive for this piece, and then they get closer and closer to 0 as we approach the point. So they start out really positive, and they get close to 0, eventually equaling 0. We don't have y values, so that's about as specific as we can get. Okay, in between -3 and -1, so through this piece, if we looked at all of those tangent lines here, what are those tangent lines doing?
They're negative.
They're all negative? Do y'all agree with that? Okay, they start out at 0, right? But then they start doing this, and then they flatten off again. So they're negative. Well, they're 0, then they're negative, then they're 0 again. So they're 0, they're negative, then they're 0 again. So, you know, how dramatic that dip is right there, there's no way for us to know. But we know they get more and more negative, and then they eventually have to start increasing back up to 0. In between -1 and +1, if we measured the slopes of the tangent line at all of these points, what's happening to those? Are they positive or negative? They're all positive. Again, we start at 0, they get really positive, and then they flatten off to 0 again.
So are all these points the derivative?
Yep.
Derivative.
Yeah. Anytime we measure the slope of this thing on a curve, that's the derivative. How steep is that little piece on a curve? That's always your derivative. So 0, they're positive, then they're 0 again. So 0, positive, and then they're 0 again. The exact shape of that, can't determine. And then after an x value of 1, what happens to all of our slopes here?
Become negative again.
Yeah. So there's 0, this slope's negative, this slope's negative, negative, more negative. Right, the slope here is even more negative. So there's 0, and they're getting more negative. So at 0, then they're getting more negative. So that's the graph of the derivative of g of x. Do y'all have any questions?
Does it mean anything the original graph looks like the leading term was like x to the 4th and the derivative one is like x to the 3rd?
Yeah, it's not a coincidence. We'll see that very clearly in 3.3. So with that in mind, the derivative on a quadratic, what do you think that would look like?
On a quadratic, it would just be linear?
Yeah, it's linear. We did do a derivative on x squared minus 5. Remember that function, x squared minus 5? We saw the derivative was 2x. Here, this is like a 4th degree polynomial. Its derivative is a 3rd degree polynomial. So this is our function, and you know, hopefully what you can, I'm just trying to get you to visualize the path that we're going to follow is the function g of x, but what we're actually measuring is the slope of the red line. The slope of the red line is the derivative at the blue point. So those are all positive, getting less and less positive until it's 0. They're 0, they're negative, a little bit more negative, a little less negative, now it's 0 again. A little bit positive, a lot positive, less positive, and 0. and then they get really negative. So that's kind of what we're envisioning when we're graphing a derivative. What is the slope of that line? I don't know if that's helpful, but you all have access to these interactive figures. In my math lab, if you just go to this multimedia library, or if you're looking at the interactive ebook online, they're already there. But you can go to multimedia library, select the chapter, select the section, and then look for interactive figures. So they're all there. Well, maybe there's another one. This one's from. So there's our horizontal tangents, where the derivative is 0. And then we'll have it draw the derivative as we progress along. What's supposed to. Okay, yeah. So the derivative's back at 0. Slope's increasing a little bit. They have to decrease back to 0 again. And then they keep decreasing. So there's our derivative. I hope that helps a little.
So it doesn't matter how high or low the middle ones go, because we don't have that?
Yeah, no. Yeah, we're not, you mean these? Or on our graph here?
Yeah.
So it doesn't matter how high or low these go, no, because we don't have y values on this, the graph of g of x. There are no y values to compare.
What would it look like if it had y values?
What would it look like, sorry?
If it had y values?
If it had y values? Well, even if this had y values, there's still not, it would be very tedious to determine, because then we have to start looking at other things on the function, which we do in chapter 4. So right now we're just trying to get something that resembles the derivative. And I mean, the one the computer generated, obviously way better than the one we drew, right? So that looks really symmetric. Ours kind of looks clunky just because we put it together in different pieces, but nonetheless, ours is very close to theirs.
So from the left in blue, you drew that it was coming down to -3.
Yeah.
Because my brain keeps wanting to read it that you should be going upwards since we're increasing, but I guess since you're saying the y values are positive, then I guess we're going down to 3?
Yeah, so the function is increasing.
Right.
The slopes are all decreasing. Because they start out like really, really steep,
Right.
and then they're really, really flat. So that's why this is decreasing.
Is it because they're like increasing through the negative values? Is that why they're like going down on the bottom one?
Over here, on the far right,
No, on
the blue piece.
Yeah.
So they're not really increasing through negative values because all of these slopes are positive, right? That's a positive slope, that's a positive slope. So that's why the graph of the derivative is up here, getting closer to 0. Remember, this piece up here, all of this is where the slope is positive.
That makes sense now.
So, right, it doesn't matter how positive they are. What matters is if they're positive, they're up here. Do y'all have any other questions?
On an exam, would you give us something without y values?
Yeah, because they should be different enough where you could get the matching fairly easy, as long as you have a basic idea of what we're actually measuring, just the slope along these paths.
Can you go back up?
Sure.
So if the slope of your derivative is positive in the middle, why is it negative when you drew it out? When it's like, I the left to the right at -3.
So why is it positive and then negative?
Your line is negative, isn't it? It's decreasing.
The red piece is, right? Or this blue piece?
The blue piece.
Yeah, they're all decreasing.
Oh, because you're approaching 0.
Right,
Ah.
right, yeah.
Gotcha.
Because these were large positive approaching 0.
Yeah.
So they're decreasing. Once we start talking about where a function's increasing and decreasing and where it's opening up or down, we're in chapter 4 when we're doing that. But we're not looking at graphs anymore to do that. We're looking at just algebraic analytic methods with derivatives to show us that or to tell us that information. So it becomes a lot less ambiguous as we move through chapter 4. Right now, this is kind of the best we can do. Oops. So really, starting off with a graph that's not linear, like the first example is linear, so you should just look for constant outputs for the derivative. Anytime you have a linear, no matter what the linear graph looks like, something like this, the graph of the derivative is going to be pieced up just by horizontal lines because every slope on that graph is constant. When we start to see more of these types of functions that we've seen previously, then that's when we want to look at, okay, well, where are the zeros? And then we got to get close with just, is it positive or is it negative? So does this graph have a horizontal tangent anywhere?
Horizontal at 0.
Right, so here, no. What about if we're tracing this out with our pencil? Somewhere in here it has to get flat, right? So, again, just getting close. At that x value, whatever this x value is, maybe it's -1/2, maybe it's -1/3, we don't know. It's just somewhere in between -1 and 0. But at that particular location, the x value is with this, and the y value of the derivative is 0, because there's the horizontal tangent line right here. Also, if your function's undefined at 1 and -1, is there any way we could find the derivative at 1 or -1? No, because you don't have a function at -1 and 1. So can we see what's going to happen with the slope of the tangent line as we get closer and closer to the asymptotes on the function itself? What happens as we get closer and closer to -1 in terms of the slope of a tangent line? Right. So at this point, and at this point way out here, the tangent line's virtually flat, right? Is it 100% flat way out here? No. Remember, this is a horizontal asymptote. We're just saying as we get further and further in the negative direction, the graph is getting flatter and flatter. It's not totally flat out here. It's not, the slope is not totally 0 out here. So it's really, really close to 0, but then what do the slopes of these lines start to do? So they're really close to 0? What is the slope of this line right here? Positive or negative? It's negative. What's the slope of this line? Negative. Is it more negative than this one? Yeah. What's the slope of this line? It's negative. Is it more negative than the previous? Yeah. So we're really close to 0, and then the slopes just keep getting more and more negative. So out here, it's really close to 0, but then it keeps getting more and more negative. Since that becomes completely vertical, then the slope of the tangent line is going to become completely vertical, somewhere down here. Scoot that over. All right, I'm just trying to keep this in line with our original graph. So they're getting more and more vertical along that first piece on the left. Are there any questions on that? Are we all able to reconcile? So that's an x value of -1. Now on this piece, what happens? We have to start over here. What are the slopes doing here? And here, and here, and here. Are they all positive or negative?
They're positive.
Yeah, these slopes are all negative, and they're flattening out to 0, right? But when we start very, very close to this asymptote up here, those slopes are almost vertical. They're getting more and more vertical. They're negative, and they're approaching 0. So we need to start down here. It's negative and approaching our 0 somewhere in here. So they're very negative, getting closer to 0. Sorry, I can't fit all of it in one screen. Super negative, flattening out to 0. Super negative, flattening out to 0. After the point at 0, what do they do?
Increase.
They start to increase, so it's flat. They're getting larger and larger, and in which direction? Are those slopes all positive or negative? Positive. So it starts out at 0 again, and then they get very positive. What happens as we get closer and closer to the vertical asymptote? What are our tangent lines doing? Yeah, approaching a positive infinity. They're getting more and more vertical as well. They start out at 0, they're sort of positive, and they're getting more and more positive. On the third piece after x equals 1, what are they doing? Right, they're getting, well, they are negative.
They're approaching 0.
Yeah, so it's like really negative here, less negative here, less negative, getting closer and closer to a horizontal, yeah, a 0. So they start out really negative, they're approaching 0. They start out really negative, they're approaching 0. Should label this f prime of x, and this is x. So there's the graph of the derivative. So, I guess it's is it missing a piece or what? I guess that's it. All right. So we're gonna, well, the horizontal tangent there. They're saying that's an x value of negative 1/3, but how are we to know that? Okay. So it's going to trace out the derivative. In other words, again, the slope of the red line at the blue point on the function. I don't know what's wrong with it. Let's try it again. Looks like it's not going to work. Anyways, if you can find the figure or pull that up, there should be something over here too, which isn't showing up. Oh well. Questions on this example? Okay, last one. Is there anywhere we would have a horizontal tangent? Negative 2 and 2, what do y'all think?
Yeah.
Here and here? Yeah, so there is one problem with that though. The function is not continuous, which means what's true about the derivative? The derivative doesn't exist. Now, two types of doesn't exist. It's either a whole or an asymptote. Are the derivatives approaching a specific value, or are they getting more and more vertical? They're approaching a specific value. The specific value they're approaching is 0. So are we going to have a whole or an asymptote? There's holes in the graph of the derivative here at -2 and here at +2.
Is there an asymptote at 0?
Yes. Yes, there is. So even though the point's not included, we're thinking about, from the right of that hole, the tangent lines are getting more and more flat, which means the y value or the y value on the derivative graph is where? At this hole. It's very close to 0. Because the tangent line is very, very flat at that point, or at that hole, rather. So here at -2, the slopes, or rather the slope at that point is pretty much 0. You can't say it's exactly 0. And then here at an x value of +2, the output is almost 0 as well. Is everyone okay with that? If that was an actual point in our graph, just like the last two, we would have just plotted a point on the x-axis. But since no such point exists on the graph, we don't have that actual point on the derivative either. So let's take care of this linear piece right here. So how do we graph the derivative of that blue piece? It's just the slope of the line. Does the slope of that line ever change? No, so the graph of the derivative here is constant. We don't have no y value, so there's no way to measure this slope, but the slope of this line is a constant. Is it positive or negative? It's positive. The slope of this line is positive. So it's just some positive constant from -4 all the way up to -2. What happens when we get to -2 on the blue piece? What happens to the tangent lines at -2? Are they defined there?
No.
No, because the function's not continuous. So whatever, I don't know that value. There's my positive c as the output of that derivative. So that's for that linear piece. Then we sort of make this jump. We've got a horizontal, and then outside of, or rather to the right of this, what are our tangent lines doing? Right, so this one's negative, a little more negative, a little more negative, a little more, a lot more. Right, so it's virtually vertical there at the origin. So starting here, they were pretty much 0, and they got really, really negative, and then to the point where we're vertical at x equals to 0. So they start out negative, get more and more negative as we get closer to this x value of 0. Does that make sense? So in the sense that our tangent lines are getting more and more vertical at this x value of 0, that does give us an asymptote on the graph of g prime. Since I did that, we'll make this a little bit longer too. What happens when we pick back up to the right of 0? What are the slopes doing?
Positive.
Right. This one's super positive, a little bit less positive, a little bit less positive, flattening out to 0. So they're very positive, getting closer to 0. So they're very positive, getting closer to 0. That's my C. Well, I'll just call it C. Very, very positive, approaching 0. And then to the right of x equals to 2, what are our slopes doing? They're decreasing. So this one's sort of negative, a little bit more negative, a little bit more negative, a lot negative. So whatever it's doing. It's not going to be linear. Well, it might be. Probably is linear. But they start out at 0 to the right of 2, and they just keep getting more negative. As far as we can tell, that's the end of the graph, so that's where we'll end our graph. Do you all have any questions on this? Yeah.
So, where you kind of wrote it purple there,
Mhm.
the third one?
Yeah.
You're showing it's going up to positive infinity?
Well, remember we got to read the graph from left to right.
Right.
So as we start over here, for these x values, the slope is really positive. But as we move this way, they get less and less positive until they're 0.
But you're putting it to where the arrow is just going upwards because there's no way to read on the y-axis. Where
Yeah.
It's actually touching. Okay.
Right, because right here, they're vertical. The tangent lines here are vertical, and then they're slowly dying off to 0. So we're like really vertical. And when we have a vertical tangent line, remember that's the slope of a vertical line. It doesn't exist because it's, and in the sense of a limit, it's infinite. You got an infinite slope. So the graph may not illustrate it, but if we were to over-exaggerate it, it looks something like this, is what that graph is doing. Does that help? Nick, was that helpful?
Yeah, I got you.
Okay. Do you all have any other questions? All right. Let's see what's next. So let's take a break before we shift gears. So the last thing we're going to talk about in this section is we're relating the idea of where a derivative exists to the idea of continuity. So the theorem says that if f is differentiable at a, what does differentiable mean again? The derivative is defined at a. So if we can define a derivative at a x value a, then f is continuous at a. So differentiability at a point implies it's continuous at a point. And you'll notice there's an alternative version to that. This is sort of the detour, it's kind of an exercise in logic. If you've ever, has anybody taken a logic class before? So if you've ever taken, I think they offer it here as, it's a philosophy class, part of a philosophy class. So logic is applied to, language or mathematics or whatever the scenario may be. They make it generic enough to apply to a broad range of things. But if we've got a if-then statement, like if today is Thanksgiving, then it's Thursday, there's other ways to rearrange statements. One being the converse. This is where we rearrange the statement. The converse of our statement is if today is Thursday, then it is Thanksgiving. So, I don't know, symbolically, the statement would be, if P, then Q. The converse is just a rearrangement. It says if Q, then P. And then the contrapositive is when we negate both arguments, I guess, in the converse. So the contrapositive is if today is not Thursday, then it is not Thanksgiving. So we just take the converse and negate both of those statements. Okay. So this contrapositive, not Q, implies not P. If you take a truthful statement and you look at its contrapositive, it will always be another truthful statement. So that's very common if you progress in math. It's very common to be presented a theorem that says if this occurs, then this occurs. It's really common to look at the contrapositive of that statement. And the contrapositive of if a function is differentiable at a, then it's continuous at a, is we take the arguments, flip them, and negate them. So if it's not continuous, then it's not differentiable. And that's the alternative version of Theorem 3.1. So the alternative version is true as well because it's the contrapositive. Of Theorem 3.1. So you notice the statement, if today is Thanksgiving, then it's Thursday, is if that's true. But if we look at the converse, if today is Thursday, then it's Thanksgiving, it's clearly not true. Today's Thursday, it's not Thanksgiving. So the converse is sometimes true, sometimes false. It really depends on the statement. Okay, so what's not true is the converse of this theorem. So it's really easy to get these things mixed up. But what would the converse of Theorem 3.1 be? If I looked at the converse statement of Theorem 3.1, the converse of this statement would be what?
If f is continuous, then it's differentiable.
Right. So the converse of our theorem is if f is continuous at a, then f is differentiable at a. So it's even though we've written that down, you've got to know that particular statement that we just wrote down is false.
Can you show an example of that?
Yeah, an example to keep this straight is the absolute value.
Okay.
Just remember the absolute value function. So if you have a hard time remembering this, just remember the absolute value. Is the absolute value function continuous at x equals to 0? Yeah, we can draw this function without ever lifting our pen when we cross through 0 like that. So this function is continuous at 0. Is this function differentiable at 0? No, because you've got a corner. The derivative, the slope of the tangent line from this side does not equal the slope of the tangent line from that side. Okay, so that function should help you remember that theorem. Does differentiability imply continuity, or does continuity imply differentiability? I don't remember. I remember the absolute value. It's continuous but not differentiable. So hopefully that's a function that we're familiar with that can help you remember that particular theorem. Do y'all have any questions on that? So not continuous implies not differentiable. Differentiable implies continuity. But, as we see in this example, continuity at a point does not imply that it's differentiable at a point. So I guess there's two ways to look at it that's true, one way to look at it that's false. So at worst, if you forget, you got a 2/3 chance of getting it right. But try to remember that absolute value graph. I think it's helpful. Okay, so an example, 2 parts, the given g of x, where is the function not continuous? Part B, where is it not differentiable? So where is our function g not continuous? At x equals to -2. Why is the function not continuous when x is -2?
There's a jump.
There's a jump, which means what?
The limit doesn't exist.
The limit doesn't exist. The function's defined at -2, but the function doesn't equal the limit because the limit from the left and right are not the same. Okay, and where else?
X equals 2.
At x equal +2. Why is the function not continuous at +2? There's a hole, which means?
The function is defined.
Yeah, right. The function is undefined. So if you're referring back to the checklist, this is not continuous because item number 2, this at x equal 2, not continuous, item number 1 in the checklist. Okay, so notice not differentiable when we're talking about where the function is not differentiable. The previous theorem said if a function is not continuous at a point, then it's not differentiable at a point. So just from the theorem alone, we automatically get these two values where the function is not differentiable. At x equal to -2 and at x equal to 2. And that's the alternative version of theorem 3.1. So we automatically get those two values. Is there anywhere else that function is not differentiable?
0.
At x equals to 0, what do y'all think? What happens at x equals to 0 on G?
The vertical asymptote.
Yeah, you have a vertical tangent line. There's 2 values of x where the function is not continuous, 3 values of x where the function is not differentiable. Any questions on that? Yeah.
Do we have to remember like the terms like infinite, discontinuity, and removable, and maybe jump for those?
For the continuity part?
Yeah.
Yeah, you should remember those. I mean, we all know we can see those visually on a graph, but describing them with the appropriate language is important too. So yeah.
Are the ends of the graph, like, is that just implied that it's not continuous? Like, you don't have to state that, right?
Yeah, so we could say that it's continuous at the ends, but only from one direction.
So doesn't that violate rule number 2?
No, because remember we had continuity defined in sense of a two-sided limit, but then we looked at continuity at endpoints, where it just made sense to look at continuity from the left, or sorry, the limit from the left and the limit from the right.
Okay.
Yeah.
Okay, that makes sense.
So yeah, there's really no issues with these endpoints. The limit from the right would exist here.
Right.
The function value exists here. The limit from the left and the function value exist here. So they're continuous, but just from one direction.
Okay.
Any other questions? All right. Well, that'll be the end of 3.2 for us. Section 3.3. Derivative rules. So I put in parentheses shortcuts because moving forward, we're no longer going to be finding derivatives using the limit as h goes to 0, et cetera, et cetera. So hopefully this first one makes sense. The derivative of any constant is 0. Again, if we think about a linear function, the slope of the linear function is always the derivative. So the slope of a constant function is always 0. In other words, at any point along a constant function, the tangent line will have a slope of 0. So the derivative of any constant is equal to 0. So notice the notation d over dx just means take the derivative of what's in the parentheses. Another example, what would the derivative of e squared be? 0. E squared is a constant. The derivative of 5 is 0.
But when we took a limit going to e squared, would it have been e squared?
Yep, so notice the limit is different. If I said here at, let's say that's an x value of 5, if I said what's the limit on this constant function as x approaches 5, from either direction it's this value, which is c. Remember the limits we looked at in chapter 2 were just general limits. I don't think we ever looked at a limit in chapter 2 outside of when we were doing the table of values that actually described a derivative. It was just a limit. Just because we put a limit on something doesn't mean we're finding its derivative, right? So if I said what's the limit as x approaches pi over 2 on the sine function, that's not going to give me a derivative. The way I find the derivative on any particular function is that I have to compute the limit as h goes to 0 on the sine of x plus h minus the sine of x all over h. That limit specifically would give me the derivative. This limit is just some y value. So don't get confused what we did in chapter 2 with just looking at limits and how they work mixed up with how we define a derivative, because I don't think we ever saw in chapter 2 an actual derivative. So it's true, the limit anywhere on a constant function is c, but the derivative, the slope of the tangent line on any constant function is always 0. Does that make sense? The difference between those two? It's really important. Next theorem is the power rule. So this tells us how to take the derivative of x to any power. For whatever reason, your textbook will keep presenting this rule over and over and over again. In order to prove this rule is true for all real numbers, I think other techniques are involved, I'm not quite sure. But your text first starts out and says, for any non-negative integer, which is integers are positive and negative whole numbers and 0. But for any non-negative whole number, the derivative is defined this way. And then in later sections, they keep refining, oh, well, it can also be a negative number. And then they present it again and say it can actually be any real number. So let's just go ahead and say that n is any real number and so this rule gives us the y behind when we look at the derivative of a quadratic, it's linear. Y when we look at the derivative of something to the 4th power, it's a cubic, and so forth. So this, to take the derivative of x to a power, the power comes out front to multiply x, and then x is raised to 1 less power than it was originally. So for example, the derivative of x squared, the power comes out to multiply x to the 1 less power than it had originally. So the derivative of x squared is 2x. So what would the derivative of x to the 5th be?
5x to the 4th.
Right, 5x to the 4th. Okay. Be mindful that the power can be any real number. So remember, the power, if it's fractional, like 1/2 or 2/3, represents a root as well. So not only does this power rule give us the derivative of all powers of x, it's a bit redundant to say, but it does give us the derivative for all roots of x as well. Like if we said, what's the derivative of the 5th root of x to the 4th, then this also covers that derivative. So the derivative of the square root of x, for instance, we've got to think about that as the same thing as the derivative of x to the power of 1/2. And then we apply the power rule to take the derivative. So what's the derivative of x to the 1/2?
1/2x to the 1/4.
1/2 x, so the power, yeah, 1/2 x. Remember, we decreased the original power by 1, so 1/2 minus 1 is negative 1/2. Otherwise, we would have to do this limit and multiply by the conjugate, simplify, let h go to 0 in order to determine that. Also, the properties of negative exponents, this is equivalent to 1 over 2x to the 1/2, or 1 over 2 root x. So the power rule does include all roots as well. Do y'all have any questions on that, the power rule? Okay. Constant multiple rule. This one's different. We're not taking the derivative of just a constant. It's a constant times a function of x. So the constant doesn't affect the derivative. Think about this as an operator. The operator says, take the derivative of everything that has an x involved. The constant doesn't, therefore the constant gets pulled out. So we're looking at this like the constant times the derivative of the function. For example, the derivative 5x to the fourth is the same thing as the derivative, 5 times the derivative of just x to the fourth. So what's the derivative of x to the fourth?
Or x to the third.
4x to the third. So that's equal to 20x cubed. I mean, the same thing is true if we just looked at that as a power rule. The 4 comes down to multiply the 5 that was already there. So we have 4 times 5 is 20, x to the 1 less power. But that's really what's happening when you do that. And some of these things may seem, like, it may seem like why even mention something like that, but all of these are theorems, which means they all need to be justified, they all need to be proved mathematically that we are capable of doing this. So we're bypassing a whole ton of work just by presenting these theorems. Otherwise, we have to do this kind of thing. Like if we want to prove that x to a power is equal to the power times x to the power minus 1, then you've got to do x to the, x to the power plus h minus x to the power all over h, and let the h go to 0. So somehow we've got to figure out how to simplify all that so we can compute that limit. So once we compute that limit, then we get this result here.
Would you ever ask us to show proofs of things?
No. Yeah, you don't have to prove things in this class. From what I hear, though, other universities, if you took Calc 1, they do have you prove things, though. So, heads up. The sum rule is really the sum and difference rule, because the difference is defined as addition of the opposite. So if you want to think about this as positive and negative, whether we're adding or subtracting. Basically, this rule is saying that if you've taken the derivative of the sum or differences of multiple functions, then the derivative operation can be distributed across sums and differences. So that's equivalent to saying that's the derivative of f of x plus or minus the derivative of g of x. So for example, the derivative of, let's do the derivative of x cubed minus x squared. What would the derivative of x cubed minus x squared be?
Okay, 2x squared minus x.
Close.
Or 3x squared.
Yeah. So we could say that's equivalent to the derivative of x cubed minus the derivative of x squared. So now power rule on both of these is 3x squared minus 2x. So notice all of those rules put together up to 3.5 is basically giving us the way to take a derivative of x to a power and or polynomial functions, right? Where it's like 3x to the 5th plus 2x to the 4th minus x to the 6th, whatever. So if we put all those together, those are all of the operations that we see involved with polynomial functions. You'll notice that in this section there isn't a derivative. How do we take the derivative of a rational function? Because there's a complete new rule for taking derivatives of one function divided by another function. So like I said, these rules come very quickly, and they all compound on one another. Finally, the derivative of e to the x. The derivative of e to the x is e to the x. So it's the only function whose derivative is actually itself. And even with some of these rules, then you can start putting these any kind of function together that we've seen in combination with multiple rules. So we could have a problem that asks us to take the derivative of the function 2x to the 5th minus 5 times e to the x plus 3. Because there's the sum and difference of functions. Here's a power of x, here's a constant times e to the x. So really all those rules culminate, we can take the derivative of this function as well. So what would the derivative of this function be?
10x to the 4th.
Okay, derivative of 2x to the 5th. The 5 comes down to multiply the 2, and it's x to 1 less power.
Minus 5 e to the x.
Yeah, minus 5 e to the x, right? Because the 5 times the e to the x, the 5 is outside of the derivative. So it's negative 5 times the derivative of e to the x, which is e to the x. And then the derivative of positive 3
0.
is 0. So there's the derivative of that function. So a lot of this stuff is now derivative rules, but don't lose sight of what the derivative is. This is the derivative function. So this says, this thing right here is the slope of the tangent line at any point on the given function 2x to the 5th minus 5 e to the x plus 3. Does anyone have any questions on those rules?
It's kind of going back just one, but if you took that equation 10x to the 4th minus 5e to the x, and you were trying to graph the derivative function or whatever, could you just plug in values?
Yeah.
See, and like if you get confused about the graph, just start plugging in values.
Yeah. So I wouldn't ask you to graph this function and its derivative. That would be a very tedious process. Maybe after chapter 4, in fact, in chapter 4 we look at how to graph these things. But right now I wouldn't say, well, here's this function, graph it, then graph its derivative. I wouldn't do that.
Okay.
But yeah, totally. In order to graph this and this, we could just plot points. It would just take forever.
It would give you that like weird derivative function though. It wouldn't give you like the regular function.
Right.
Yes.
Yeah, so this is the derivative function. This is,
Okay.
yeah.
Okay, that makes sense.
So if we looked at x squared, and its derivative is 2x. Right. So we're thinking about prior methods. I mean, this is a lot more simplistic than that last example, but we're measuring the slopes of the tangent line. It's, as we get out here, it's very negative. They're a little bit less negative, a little bit less negative, and then there's 0, right? So they start out negative, they start out down here, they get closer and closer to 0, and then after 0, they get more and more positive. So that's why we see the graph here as 2x. So they start out negative, then they're 0, and they're positive. But notice on a parabola, on any parabola, it's a constant rate of change in terms of x. So like the rate of change is always 2x, whereas something like this, the rate of change isn't always 2 times the x value, right? It's exponential when it's compared to x. Uh-oh. Did anyone print this out? Do you have stuff after the first page?
Yeah.
Did stuff print off?
Yeah. There's like 4 or 3 other pages.
Yeah.
See what the deal is. I don't know why these are blank. That's unfortunate. This one has it. So I think that's good. All right.
I'm excited to finally be able to use the 4K. It's like my whole computer couldn't handle it. Yeah.
All right. Sorry about that. I don't know what happened.
The Adobe Premiere. It's like $20 a month.
Okay, so first example, write the equation of the tangent line for the given function at the given point, and then find the point or points on the graph of f of x where it has a horizontal tangent, or where the tangent line is horizontal. So when we see this now, equation of the tangent line, what do we need? We need the slope of the tangent line. How do we find the slope of the tangent line? Take the derivative. So the first thing we need to do is find f prime of x. So remember, this is the slope of the tangent line at any point xy on the original function. So why don't you take a minute or two and think about the derivative of f of x. Anybody got it? You need him another minute. Oh no, I'm just showing you. This is how we previously would define the derivative versus the shortcut. So even though there's a lot of shortcuts to remember as far as formulas go, at least it keeps us from having to mess with all of this stuff. So shortcut way, the derivative of that function is what?
2 minus 1/2 e to the x.
Okay. Do y'all agree? 2 minus 1/2 e to the x. So let's look at it step by step. Hopefully at some point you get to get to a level where you don't have to look at it step by step. But since we're just now learning these derivative rules, that derivative then of 2x minus 1/2 e to the x, well, there's a sum and a difference, or a difference rather, so we can write that as the derivative of 2x minus the derivative of 1/2 e to the x. Do y'all agree? There's a constant times a function of x, so that's 2 times the derivative of x. There's another constant of 1/2, so minus 1/2 times the derivative of e to the x. So think about x as x to the first, right? It's 2 times 1 times x to the 0th power. X to the 0th power is 1. So that's just 2 times 1. We have a minus 1/2 times the derivative of e to the x, which is e to the x. So we just have minus 1/2 e to the x. So 2 minus 1/2 e to the x derivative. Does anyone have any questions on that? Okay. So there's the derivative at any point on that function. We're specifically asked to find the derivative at the point 0, negative 1/2. So really, step 1 was to find this. Step 2, we're computing the derivative evaluated at an x value of 0. So what's the value of 2 minus 1/2 e to the 0? Is what?
1.5.
Right, 3 over 2.
I have a question.
Sure.
So, like, what if you set the equation that you found as a derivative to 0? What does that find you?
Okay, we'll talk about that in a second.
Okay.
Yeah.
Because I accidentally did that.
Okay, good. So let's remind ourselves what this actually means. The derivative at an x value of 0, that is the slope of the tangent line, negative 1/2. So that's the slope of the tangent line at that point. I'll make that one red too. Okay. Questions on that? So now we can write the equation of the tangent line because we have the slope of the tangent line. Equation of the tangent line at the point 0, negative 1/2. Point slope form, y minus the y coordinate equals to the slope of the tangent line, 3/2, times x minus the x coordinate. So y is 3/2 x minus 1/2. So that is the equation of the tangent line. So if we look at the function 2x minus 1/2 e to the x, we have this function at the point 0, negative 1/2. So the first thing we measured was how steep is the graph there at that point, was 3/2. And then we constructed the line. See, notice the y-intercept of that line is any different, then it's no longer tangent to that point. It specifically has to be at 1/2. Does anyone have any questions?
What's the other equation then? The like 2 minus 1/2 e to the x?
2 minus 1/2 e to the x?
Yeah.
So 2 minus 1/2 e to the x is what?
Like what would it look like compared to the others?
Oh, so this, remember this, the graph of the derivative, or the derivative is giving us the slope of the tangent line at any point. So like if we looked at this graph and I said, what's the slope on this function at 2.314? Then we have to go back to the derivative and plug in 2.314 here for x. What's the slope at 2.153, comma 0? Well, I plug in 2.153 into my derivative. Right, so just remember the derivative gives you the slope at any point as long as you plug in that x coordinate of the point. Specifically, we wanted to know what the slope was at the point 0, negative 1/2, so we plugged 0 into our derivative. Okay. The second portion of this problem says to find the point or points on the graph where the function has a horizontal tangent line. What values of x does f of x have a horizontal tangent? So what value or values is the question we're answering. So does everyone see on the graph, the purple graph there, that we do have a horizontal tangent line at the apex of this function? Yeah? So what we're going to do is find that. What is this x value here that corresponds to that point that's here? So what is that x value? Yeah. And how do we find that?
So you set the derivative function equal to 0.
Equal to 0, right? Horizontal tangent line. Well, in order for a line to be horizontal, what is its slope? 0. So the slope of the tangent line at any and all points, in order to be horizontal, has to be 0. So anytime you're asked to find a horizontal tangent line, that's the process. You take your derivative, you set it equal to 0, and you have to solve for x. So our derivative was 2 minus 1/2 e to the x. So where does 2 minus 1/2 e to the x, horizontal tangent, where does our derivative equal 0? So this is where all of this stuff where you have to solve exponential equations, trig equations, logarithmic equations, primarily in the context of calculus, they show up when we want to know something about the derivative. Where is the derivative horizontal? Where is the slope of the tangent line equal to 12? Those all involve you solving equations. Depending on what kind of derivative you're dealing with, and you're back to solving here, an exponential equation, could be trig, could be whatever. So there's only 2 terms here. We subtract 2, multiply by negative 1/2, so that we have e to the x equals to 4. Y'all remember how to solve that?
Natural log of both sides.
Yeah, the inverse of e to the x is the natural log of x. So an ln of e to the x is x. So x is the natural log of 4, which is, natural log of 4 is approximately what, 1.3, what was it, 86?
Yeah, 86.
86, 1.386. So when x is approximately 1.386, the derivative is 0. In other words, the slope of the tangent line at this x value is 0. So we're going to say that f of x has a horizontal tangent, line when x is the natural log of 4. I mean, of course, if we were looking at that graphically, the graph tells us what that point is, right? But the idea is that we don't have that graph. So going back to the graph here, horizontal tangent line right here, an x value of 1.386. So that's our natural log of 4. So please remember this for horizontal tangent. Not as prevalent in chapter 3, but in chapter 4, we do a lot of this stuff. Does anyone have any questions on this example? Seeing these shortcuts, if you haven't done 3.1 or 3.2's homework, when they ask you to find the derivative, you especially in 3.2, use the definition of the derivative. Although it takes a long time, you're still going to be tested on that. So if it says find the derivative in 3.2 of 3x squared minus 2x, the first problem we looked at, don't just take the derivative using the shortcut. It's section 3.2, so use the definition. On the exam, I'll explicitly state Find the derivative using the definition. There'll probably just be one problem like that. Any other derivative, you can use these shortcuts. But still, you need to know how to use the definition of the derivative to find a derivative. Don't use this section as an excuse to fly through section 3.1 and 3.2 is what I'm saying. Actually do the work that was presented in 3.1 and 3.2. So some other examples. Find the derivative of the given function. So what's the derivative of e cubed?
Zero.
Good, 0. F prime is 0. E cubed is a constant. You can always tell you have a constant because there aren't any x's that show up. You know, on a different note, not that we would see it, but if you were asked to take the derivative of 3 plus y plus z plus w to the 5th with respect to x, there is no x here. All of those things are constants in terms of x. So that derivative is 0 with respect to x. But just make sure you're not confusing that with, like, take the derivative of, like 5e to the x. Now we've got an x showing up. The 5 is a constant that can be pulled out of the derivative, but we still have the function of x to take the derivative of. Is everyone clear on what I'm saying there? Also, another thing that I see is don't get exponentials like e to the x confused with like x to a power. This is a power rule. As we'll see later, this is no longer a power rule because x isn't a power. X is now in the exponent. So here, let me erase this. Make this 2. So power rules applied to this, completely different rule applied to exponentials. I see those things confused a lot. Function 2, the square root of x over 3. Find the derivative.
Are there rules for multiplying and dividing?
Yeah, those are in 3.4.
Oh.
But the division by 3 is fine because that's just a constant. So this is actually 1/3 times the derivative of the square root of x. We already looked at the derivative of the square root, but in case you forgot, we turn that into a power. That's 1/3 times the derivative of x to the power of 1/2. And then we use the power rule. So the 1/2 comes out to multiply x, and we subtract 1 from the original power. So we would say that the derivative f prime is 1/6 x to the negative 1/2.
Do you care which way we write it?
No, typically, I don't think there is a standard way to do this. If it does say write with positive exponents, then we would want to write it as 1/6 x to the positive 1/2.
Would it be fine to put in the radical?
Yeah, I'm fine with the negatives, or 1/6 root x. I personally don't care. Just for my math lab, be aware of their instructions. They might tell you to write it one way or the other. questions on that second example?
Does that mean that either one of those three is gonna be giving us more credit on the exam?
Which one?
Like,
Oh, yeah, either or, yeah. I think the only time it starts to affect your work is like, if something comes along, like this term and another term with a negative exponent, and you have to solve where that equation is equal to 0, it's more beneficial to write it out like this so you can factor out. But how we write it doesn't matter. All right, so you'll notice number 3 and 4 and 5 are either products of functions of x or quotients of functions of x. So we actually don't look at the product rule and the quotient rule until the next section. But this is here to always remind you that if you can simplify the function before you take the derivative, you want to do that because you're dealing with something simpler to take the derivative of. So this function, and after 3, 4, we'll know how to take the derivative of it as it is because it's the product of two functions of x. But for now, what we have to do is simplify this first. In fact, if you can simplify it first before you take the derivative, it will always be an easier derivative to take. So we have x to the 1/2 times x. So that's going to give us what? What do we do with exponents there? X to the 1/2 times x. You add them. So that's x to the 3/2 minus x to the 1/2. Just don't lose track of where you're at. We've just simplified f of x. We have yet to take the derivative. So we simplify f of x, then we can use the power rule on both of those. So what is the derivative of x to the 3/2?
3 root x over 2.
Yeah. So the power comes out, multiplies x to the 1 less power. What's 3/2 minus 1? 1/2. Same thing here, minus the derivative of x to the 1/2, which is 1/2 x to the negative 1/2. So as far as the derivative goes, that's it. How we present the derivative with positive or negative exponents. Totally up to the question, I guess. Anyone have any questions on this? The example 4 and example 5 are the same way. We don't know the derivatives of those, so we have to simplify them first before we take the derivative. So see you all Tuesday. Have a good weekend.